Howdy shipmates! Welcome to the third lesson on circles, pure chapter 6.3, the third of 4 lessons. Today we're going to be having a look at proving some circle theorems from GCSE, but I will just say now, don't worry about regurgitating or remembering these proofs. It's just to try and drill home that they do come from somewhere, they're not just made up, and just to help you remember them for future use. But the actual proofs, you do not need to remember these. Okay? Not for A level. I do not think you'll be asked to reproduce them. In fact, I'd bet you wouldn't. So what we need to do is, as ever, get warmed up with some warm-up questions. Here they are. So try these first. Press play once you've done them all, or attempted them all at least, and see if you've gone wrong, or hopefully where you've gone right. So let's have a look now at the solution to question 1. Question 1, we're asked to state the equation of a circle of centre 4, 6, radius 2 root 7 in this standard circle form. So what we need to remember is that when we have an equation in this form, we're effectively told what the centre is and the radius is. What I mean by that is this A parameter here corresponds to the x coordinate of the centre, the parameter B corresponds to the y coordinate of the centre, and R is the radius. So we actually know all we need. We just need to plug it in this form. So we're going to have x minus 4 all squared plus y minus 6 all squared equals r all squared, which is 2 root 7 all squared. So all I've done there is just substitute in what we know. So we know r is 2 root 7, the x coordinate of the centre is 4, and the y coordinate of the centre is 6. So the only thing we need to do now is just expand out this bit at the end. So that's going to give us x minus 4 all squared plus y minus 6 all squared. 2 squared is 4, root 7 squared is 7. So 4 times 7 will give us 28. And if you don't like that, please do feel free to use a calculator to verify it. Question 2. Find the centre and radius of a circle with equation x squared plus y squared plus 6x plus 10y minus 15 equals 0. What we need to do here is to get it from this expanded out form into factorised form. And so what we do to do this is complete the square for the x terms and x squared terms and the terms relating to y separately. We can leave this minus 15 alone for now. And so the x terms, let's deal with these first. So completing the square on the x terms, we take the x squared and just put the x in brackets. We half the coefficient of the x, so half of plus 6 is plus 3. We then square that and minus off this term all squared. So 3 squared is 9, so we subtract off 9. Next, we do the same for the y terms. So the y terms, we take the y squared and just put 1y in brackets, and we half the coefficient of the y, so half of positive 10 is positive 5. We then square that, and minus off this term all squared, so 5 squared, we minus off 25. Don't forget about minus 15 at the end. We have it equal to 0. So this can now be rearranged further. So we have x plus 3 squared plus y plus 5 all squared. Now minus 9 minus 25 minus 15 is minus 49. So if we add 49 to both sides, we get 49. So this is now the standard form, so we're effectively told what the radius is. So the radius is root 49, which is 7. And the centre corresponds to the numbers in the brackets. So all we need to do here is look at the numbers and switch the signs. So plus 3 becomes negative 3. Plus 5 becomes minus 5. Number 3 of a warm-up, we've got this table showing the heights of 100 students, and we're asked to calculate an estimate for the median height of a student, and to give the answer correct to 1 decimal place. So this is going to be a job of interpolation. Remember, the class whiz is very powerful, can do loads, but it can't help us when it comes to estimating positions, measures of position in grouped frequency tables. So here, the class whiz would generate a mistake. We need to use this process of interpolation and do the work manually. So the first suggestion is what I'd do here is to write down the limits on the class intervals. So starting at 120, the lower limit here is obviously, like I've said, 120. The next boundary is 130, 140, 150, 160, and the upper limit here is 170. We then do a list of cumulative frequencies. So always start with 0 with cumulative frequency, add 8, 8 plus 16 is 24, 24 plus 25 is 49, 49 plus 30 takes us to 79, and finally 79 plus 21 is 100. So we're asked for the median. Median is halfway. So if there's 100 values, we're going to do 100 divided by 2 to find the halfway point. And obviously 100 divided by 2 equals 50, which tells us, therefore, that the median must be the 50th value. It's now a question of whereabouts does this 50th value lie. So we look at these cumulative frequencies and keep going until we get to a number which is less than 50 at one end and then more than 50 at the other. So basically between which two numbers is 50 in between. You can see here 50 is more than 49 but less than 79. That tells us that the median must be in this interval. So because it's 50th, we can therefore say the median is in this one. So it's in 150 to 160. And more than that, we can work out the position, the estimated position of the median in this interval. So the median is number 50, the 50th value. This class interval starts after the 49th. So after the 49th, the first one is the 50th. 50 minus 49 is 1. In other words, the median is going to be the first value out of 30 in this interval. If you're wondering where I've got 30 from, it's simply because 30 is the frequency of this interval. And so the median is the first one out of 30. So we're going to use this fraction in a moment to work out an estimate of our median. So the estimate of our median, we're going to start where this class interval starts. It starts at 150. Now because it's the first one out of 30, we're going to add on 1/30th, this fraction here, add on 1/30th of the class width. So from 150 to 160, that's a class width of 10. And so if we calculate this now, we're going to have 150 plus 1/30 multiplied by 10, and to 1 decimal place, that gives us 150.3. So the estimate of our median is 150.3 centimetres. We can now have a look and think about the last one in the warm-up, question 4. Well, question 4, it asks us about the same table as in question 3. It asks us to calculate an estimate for the standard deviation of students' heights. I'm going to show you both ways of doing this. The manual way well, semi-manual, it still involves a calculator, and I'm going to show you the very quick way which you can do using the class whiz to its full power. So let's do this the first way, semi-manually, using the formulas for standard deviation. So just to remind you of the table, here it was from before. Now we need to work out a few extra bits and pieces for this. First of all, what we need to work out is the midpoints of each interval, and then we need to add in columns for fx and fx squared. And so we need to have 3 extra columns, or at the very least 3 extra spaces for these 3 extra components for our calculations. So you might want to do something like this. We've got spaces for midpoints, fx and fx squared. First of all, doing the midpoints. So we just calculate the midpoints for each one of these intervals. So to cut a long story short, we do this number plus the n number, so 120 plus 130, then half them. That's all we do to find the midpoints of these. So the first one, for example, 120 plus 130 is 250. Half of 250 is 125. So doing the same method, just going down for each of these, you should get this for the midpoints. Now the fx column, what we're going to do next is we take these midpoints and multiply by the frequency. So fx, in our case, just stands for each frequency multiplied by the midpoint. So all we're going to do here, first of all, for example, is 8 multiplied by 125, 16 times 135, and so on going down. And that'll give us the answers for this column here. So you might want to do this yourselves and just compare it with mine. What you should have got is these values here. Okay. So you should have got these values here, and then fx squared, what we're going to do next is we're going to take the frequency and multiply by the midpoints squared. So the first one would be 8 multiplied by 125 squared, which will give us this answer here. Then 16 times 135 squared will give us this answer here, and so on. So the next and final column, you should get this. These numbers. Finally, what we're going to do is we're going to total these up. So we're going to total the frequencies, total the fx's, total the fx squareds. We're not going to total the midpoints because that'll just give us a nonsense, to be honest. So let's have a look what we get next. As I say, we might want to just block this one out just to let us know not to do anything here. If we total up all these columns, this one, and this one, we're going to get something like this. So just check at this stage if you've got that. Next up, we're going to use these totals, these values, and input them into the table for working out standard deviation from a grouped frequency table. The formula, which you've seen before, is something a bit like this. So this is for tabulated data. So we're now good to go in working out our estimate for standard deviation. So standard deviation is the sum of the fx squared, so it's this total here. So 2234 700 divided by the total of the frequencies. This just means the grand total of all your data values. So here, there was 100 students. So the grand total of frequency is 100. Now this here is essentially just the mean. So we're minusing off the mean squared. So it's the sum of the fx's. So it's going to be 14900 divided by 100. That whole expression squared. So if we just use our class whiz at this stage, so it's the square root of 2234700 over 100, then minus, put it in brackets, 14900, whoops, one too many zeros, all over 100 squared. Press equals. We see here we get to 3 significant figures, 12.1. So an estimate of our standard deviation is 12.1 centimetres, and that's correct and fine to 3 significant figures. So that's doing it the longer method, using the formula and a bit of calculation here, which takes longer. The quick way of doing it is with the class whiz, which I'm going to show you now. Using the class whiz, what we'd still need to work out the midpoints. Even with the class whiz, we need to do this stage ourselves. But after that, we can now use the class whiz. So I'll show you how to do this now. So you get your class whiz out. I'll show you how to do this step by step. I'll put it on the big screen as well, so you can see all the steps here I'm doing clearly. We're going to press menu. We're going to scroll down to option 6, statistics. We press equals. We want a one variable calculation, so press 1 for one variable, and we get this. You need to make sure you've got a frequency column. If you've not, I'm going to show you how to get this column. You press Shift, Menu, should get this menu here, scroll down until you can see this statistics option, and press option 3. You then want to turn this frequency column on, so you press 1 to turn it on. Likewise, of course, if you wanted to get rid of it, you could press 2 to turn it off. I'm going to press 1 to turn it on. As you can see, there it is. If I wanted that to disappear, I would have pressed option 2, and it just reduced down to this first column. For the x's, we're going to type in our midpoints. So our first x, if you like, is 125, then 135, 145, 155, and finally 165. We're then going to scroll back up and type in these corresponding frequencies. So the first frequency is 8, after 8 it's going to be 16, then 25, then 30, and the last one, I've slightly hidden it, I think it's 21. Yeah, the last one's 21. Press equals. Once you've typed in all your data, we press AC. So press AC to clear it all away, then we press OPTN, and then we're going to press option 2 to bring up the calculations based on our one variable. So press option 2. As you can see, you've got different calculations worked out for us. The one we're interested in is this sigma x, which stands for standard deviation, and as we had before, but just in a much quicker way, we can see the standard deviation to 3 significant figures is 12.1. So using the class whiz, again we get 12.1 centimetres. I'll give credit where credit's due to the class whiz. So that concludes our warm-up. So now the warm-up's done, we can now get on to the main body of the lesson. So let's now have a look and talk through what's in store for us today. Okay, so let's start with some circle theorems. So you will have no doubt encountered several circle theorems on your journey through GCSE maths. All of them can be proven, as you'd obviously expect. If it couldn't be proven, it would be quite ridiculous. We start by proving the most useful of these theorems so that we may apply their results with greater confidence. And so if you understand them, I do believe it helps you to remember them. So let's have a look at some. By the way, a little note, do relax. Proving these theorems, they're not going to ask you to do that in your A-level exam. They'll ask you to apply the results, not prove the results. So first theorem I want to have a look at with you is the angle in a semicircle is a right angle. This is a standard result that can be proven. So I'm going to talk you through step by step how we can construct the proof and arrive at the result. So first of all, draw the problem. So I've got for you on your handout a pre-drawn circle. So what you need to do here is to draw in a diameter and then construct, using this diameter, any triangle with the third point which touches the circumference. So I've done it up here. You can do it down here or anywhere you want, as long as you've got 3 points, 2 of which make a diameter and the third one is any other point on the circumference. The second step, you need to label the angles here, here and here, and the radii. So what I mean by this If this is the centre of a circle, we're going to have a radius here and here. And these angles, we can label them as well. So that's a radius, this is a radius, and the angles are going to be A, B, and C. It's quite arbitrary how you label them, but I think A, B, and C work absolutely fine. So now we're beginning to form a picture of what we need to do, but we're not there yet by any means. Step 3, we need to add in an extra radius. So what we're going to do here is we're going to bring an extra radius up from the middle to this point on the circumference at B, like so. Next up, we're going to generate some equations and finish off this proof for ourselves. So we've got here angle B. Okay, so what I'm going to do here, I'm just going to take angle B to the side, because in a moment it's going to be swamped with a few extra bits and pieces. So that's angle B. So I'm just going to make a reminder, that whole angle is B. We're going to split B into two smaller angles. I'm going to call this triangle 1. I'm going to call this triangle 2. So if you just have a look at triangle 1 for a moment, it's a triangle and two sides are radiuses. You've got two sides which are radii, so therefore triangle 1 is isosceles. So we can write this down. So we know that the base angles of an isosceles triangle are equal. And so where the two sides that are equal meet is the odd angle out. So this one isn't the same as the others. But if this one's A, then this angle here, that's going to be angle A as well. So I'm just going to colour code this. So this tiny portion of B, which falls inside triangle 1, that's going to be angle A. So what I'll do here as well, I'll just colour code in the original angle A as well. So all I've said here is that triangle 1 is isosceles. So whatever angle A is, it's the same size angle at the top. So triangle 1 is isosceles, but if I have a look at triangle 2, this is a triangle with two sides which are a radius, so that's also going to be isosceles. So triangle 1 is isosceles, and triangle 2 is isosceles. So on triangle 2, if this one's C, the other base angle over here will also be C. So I can label this C and draw in what C is. So the portion of B inside triangle 2, because it's an isosceles triangle, has to be C as well. So that's C, as is the angle at the top of triangle 2. So triangle 1 is isosceles and triangle 2 is isosceles. We've used that fact to show that therefore angle B equals angle A plus angle C. We now need to consider the whole triangle. So consider the triangle ABC. So for triangle ABC, obviously for any triangle we know this very well, the sum of all the angles in a triangle add up to 180. And so A plus B plus C will add up to 180, quite obviously. So A is in green, B is the angle which is in yellow, and C is this blue one. But we said that B was the same as A plus C, and so actually what we can do here is we can say that B is A plus C. So we've got A plus B, but B is A plus C. And plus C again. Equals 180. So we've actually got A plus C plus C. So we've got 2 A's plus 2 C's equals 180. If we divide all this by 2, we get that A plus C equals 90 degrees. But just remember, B, which is the angle in the semicircle, B is A plus C. So B equals 90 degrees, because A plus C, the green and the blue, that is B. So just remember that. So A plus C is 90, but that is what B is. And so B, because it's A plus C, is 90 degrees. So we've shown that B is 90, so we've proven it. So all we need is just a concluding statement, something along the lines of, therefore, the angle in the semicircle, the angle which is not involved in the diameter, the angle which is touching the circumference and joins up either side of the diameter, is called the angle in the semicircle. The angle in a semicircle is a right angle, because we've proven it's 90 degrees. And 90 degrees is, by definition, a right angle. Little square symbol means we're done. Let's have a look at the second theorem. A tangent is perpendicular to the radius where it touches the circle. So, first of all, draw a circle, a tangent, and a line joining the tangent to the circle's centre. So you've got this on your worksheet. First thing we need to do is to draw a radius which is touching this tangent, like so. Next, we have to assume, this is a proof by contradiction, we're going to actually assume that this radius is not perpendicular. So we're going to assume that the perpendicular line joining a tangent to the circle's centre is not a radius. So we're assuming this is not perpendicular. So we're going to do another diagram and think, well, if this isn't perpendicular, let's draw a different line that is. So that's what we've got so far, just shrunken down. Let's say if that isn't a perpendicular line, maybe a different one at a slight sort of angle coming off is. So let's say this one is. If our assumption's wrong, let's say this one is perpendicular then. So, bit of labelling, call that centre O, we'll call this B, that's C. D is the point that OC goes through where it touches the circumference. And so OD is a radius which is the same length as OB. So from D to C is a tiny bit extra so that it touches the tangent. I'm going to label this tangent as well with different letters. I'm going to label this tangent section AE. So let's think about this carefully, and we're going to arrive at a contradiction. We'll arrive at a nonsense which contradicts our assumption that this is not perpendicular. And if we get nonsense by assuming that it isn't, it therefore means that our assumption is wrong and it is perpendicular. So let's just construct this and think about it step by step. So let's assume that OC is perpendicular to AE. In other words, when we construct this carefully reasoned proof, we're going to suppose that OB, this one here, is not perpendicular. We're assuming OB is not perpendicular to the tangent. And we're supposing instead that OC is perpendicular to AE. So that's the first thing we're going to say and assume. Next, we could say that from this assumption, angle OCB, this angle here, must be 90 degrees. Okay, because we're saying that is perpendicular and that isn't. And because it's a triangle, that's 90 degrees. These other two are going to be acute. And so this angle at B is acute. So because we're assuming this is a right angled triangle, we're assuming that the right angle is here. In this right angled triangle OBC, OB, this one here, must be the hypotenuse. Remember, the side opposite to the right angle in a right angled triangle is always the longest side. So using our assumption, OB is the longest side, and so OB is longer than OC. However, just look at this diagram and think about it. We can clearly see from this diagram that C lies outside of the circle, as would every other point for that matter along AE, apart from B, which is on the circle. So in other words, actually OC has to be larger than OB. OB is a radius, as is OD, but we have to go this extra bit longer from D to C to get to the tangent, so OC is obviously going to be longer than OB. So we had OC is less than OB, but now looking at this diagram, it's clear that OC is greater than OB. So this is contradicting each other. So this contradicts the initial result we had, that OC is less than OB. If we've got a contradiction and our steps have been completely logical, which they have, we've got to have a contradiction if our initial assumption is rubbish. So our initial assumption must be wrong, because we've thought this through carefully and we've arrived at a nonsense. OC is less than OB, but also it's greater than OB. That's just absolute rubbish. So what was our initial assumption? Our initial assumption was that OB is not perpendicular to the tangent. We were saying that this is not perpendicular to the tangent, and we've formulated some absolute garbage which makes no sense. So this initial assumption here must be wrong. It's wrong to say that OB is not perpendicular. The only conclusion therefore is that it must be right to say that OB is perpendicular to the tangent. So in other words, OB has to be perpendicular to AE. That's the only logical conclusion. So proof by contradiction, you sort of set out to prove that something which you know is true is not true. You arrive logically at some absolute nonsensical rubbish, which proves that your assumption that what is true is not true must be erroneous. Therefore, what is true is proven to be true. A bit to get your head around, maybe replay this and just think about it through carefully on your own and in your own space. The third one, the perpendicular bisector of a chord passes through the centre of a circle. So again, you've got this diagram pre-drawn in your notes. So first of all, what you need to do is to draw a chord in the circle. So just draw a straight line connecting 2 points on the circumference. I'd suggest not going through the centre. So just any 2 points joined together with a straight line. I've done mine like this. You don't have to do yours like this, you could have drawn it anywhere, but like I say, ignore the centre if you can. Second step, connect two radiuses to the chord's endpoints. So we need a radius here and a radius there. So one radius joined in, then the other. Step 3, we're going to bisect the chord so that the bisector passes through the centre of the circle. So we're going to split this chord in half so that the bisector also passes through this centre, like so. This looks to be perpendicular to the chord, this bisector, but we're going to prove that it's going to be perpendicular as well as being a bisector. All we've done now is split it in half. We don't know yet that this is definitely 90 degrees. This is what we're going to prove. So step 4, we're going to construct a geometric argument to prove that such a bisector must be a perpendicular bisector. So what we could do with some labels. First of all, because it's a bisector, this line is the same length as this line. So we can add dashes to denote that these sides are of the same length. In the same way, this length is a radius and this length is a radius. So they've got to be the same length. So we can add in these two dashed lines here to denote that. Let's just label these points. So we've got two triangles here, OAC and OBC. We can see that OA must equal OB because both of those are radii. So that's obviously true. As well, AC is the same as BC because we bisected the chord in the first place. We split it in half in equal bits. OC, this line from O to C, is a common side, common to both triangles OAC and OBC. So these triangles here and here have three sides which are the same length, a radius, AC and BC, and this shared side. So what this means is that the triangle OAC has to be congruent to triangle OBC, using the idea of side, side, side congruency. So therefore, because they're congruent, this angle here, ACO, must be the same as angle BCO. But if you notice, A, C, and B lie on a straight line, and we know that angles on a straight line add up to 180 from GCSE. So because the angle around C is 180, the angle ACO, this one here, is the same as BCO, this one. So these two are equal, yet combined they add up to 180. If they're both equal, it must be the case that each is 180 divided by 2, which is 90. In other words, this one here is a right angle, and this one here is a right angle as well. So this bisector makes a perpendicular angle with a chord. So it's a bisector which is perpendicular. In other words, it's a perpendicular bisector. So therefore what we can say is that this bisector of a chord that goes through the centre of a circle is a perpendicular bisector. That's one way of saying it. To word this in a slightly nicer way, which is more like the theorem we want to prove, if we just rejig the word in so it words in a nicer way, we can say that therefore the perpendicular bisector of a chord passes through the centre of a circle. And that's that theorem completed as well. So now we've proven some circle theorems, we're not actually going to use these now. We're going to use them in the next lesson mainly. What I want to mention before we finish this lesson is about the discriminant, and in particular the fact that we don't only use the discriminant when it comes to standard quadratic equations. It can apply to circles as well, so let me explain. So we've seen in earlier lessons, in the quadratics chapter, how we can use the discriminant to determine the number of solutions to quadratic equations. But because the equation of a circle involves two variables, both raised to the power 2, it involves x squared and y squared. Often we can reduce an equation of a circle to a simpler quadratic using substitution and algebraic manipulation. So we can use the discriminant and a combination with substitution to see at how many points a straight line, let's just call it the standard y equals mx plus c, meets a circle. If we sub in mx plus c in place of y into the standard circle equation, what we yield is this quadratic here, x minus a all squared plus mx plus c instead of y minus b all squared equals r squared, where in the same way as before, a and b are the centre of the circle and r is the radius of it. So this quadratic, which we have here, we can then expand it and simplify it and work out its discriminant. So what about the discriminant of this? So one possibility, is that this discriminant is greater than 0. And if that's the case, then the line y equals mx plus c, which we've substituted into this formula, must intersect the circle at 2 distinct points. This is the same idea as the discriminant what we saw before. When the value of the discriminant is greater than 0, there's 2 solutions. Only here we're interpreting those 2 solutions as 2 intersections of the line with the circle. Another possibility is that the value of a discriminant is less than 0. Now if the value of a discriminant is less than 0, much in the same way as with quadratics, we have no solutions. So in this scenario, it means that this line y equals mx plus c does not intersect the circle at all. In other words, it doesn't meet the circle at any point. If, however, the discriminant is exactly equal to 0, what this means is that the line y equals mx plus c touches the circle at one precise point only, and that is essentially the definition of a tangent. And so we can prove if a straight line is tangential to a circle, cuts it at 2 points, or doesn't meet the circle at all, using the discriminant. And so we see now how the discriminant has much more power than what you may have thought it did. Let's have a look now at some examples, the last of which is a very big challenge, but I'm going to talk you through it, so then no need to panic. So first of all, work to example 1. We're told the coordinates of the points where the line y equals x plus 5 intersects the circle x squared plus y minus 2 squared equals 29 need to be found. So like I mentioned in that last section, what we can do here is substitute in for y into this formula for the circle. And so if we do that, this formula here becomes x squared plus x plus 5 minus 2 all squared equals 29, because all I've done here is subbed in the expression x plus 5 in place of y. Now this can obviously be simplified, so we have x squared plus, well, x plus 5 minus 2, that's just x plus 3 all squared equals 29. We can now expand this out, so we have x squared, expand out x plus 3 all squared, we have x squared plus 6x plus 9 equals 29. So if we simplify and rearrange so it becomes a quadratic equal to 0, we're going to have 2x squared plus 6x, and then 9 minus 29 will give us minus 20, and that's going to be equal to 0. Now all these coefficients, you should notice, all have a factor of 2, so we can divide through the whole thing by 2 to get x squared plus 3x minus 10 equals 0. So what we can do here is actually factorize this. So two numbers that multiply together to give minus 10 and add up to positive 3, they're going to be positive 5 and negative 2. So therefore, this line is going to intersect the circle. It's going to be intersections when x is equal to minus 5 from this one, and from the second bracket when x is equal to 2. Now we can use the fact that y is x plus 5 to work out the corresponding values for y. So 1 is x minus 5, so if we add 5 onto this, we're going to get where y is 0. And when x is 2, 2 plus 5 gives us that y is 7. So these are essentially our answers. But we are asked for these as coordinates. So just to be good students, let's write them as coordinates. So they intersect at -5, 0, and at 2, 7. Worked example 2, we've got Brutus thinking that the line y equals x minus 7 is a tangent to this circle x plus 2 squared plus y squared equals 33. We need to show that Brutus is wrong. So what we can do here is sub in that y is x minus 7 into this expression for y here. So this equation here, we can write in a different form and say that it's the same as x plus 2 all squared plus x minus 7 all squared, because that's what y is, according to this, where it hits the curve. That needs to be equal to 33. So let's expand this out and simplify. So x plus 2 all squared, we get x squared plus 4x plus 4. This bracket, we're going to get x squared. X times minus 7 is minus 7x. Double that gives us minus 14x. Minus 7 all squared is positive 49. And that equals 33. So let's neaten this up a bit. We've got x squared plus x squared. So we're going to have 2x squareds plus 4x minus 14x. That gives us minus 10x. 4 plus 49 is 53. So when we subtract 33 from both sides, that's going to leave us with positive 20. That equals 0. Again, like before, all coefficients are even, so we can half everything. So dividing through by 2 gives us x squared minus 5x plus 10 equals 0. This doesn't factorise in any obvious way, so we can start to wonder if it has any solutions at all. Well, we can check the discriminant of this. So the discriminant is going to be b squared minus 4ac. In this case, b is minus 5 all squared, and minus 4 times a, which is just 1, because it's just 1x squared, times c, which is 10. So that gives us 25 minus 40. 25 minus 40 is minus 15, which the main thing to notice is it's less than 0. Because the discriminant is less than 0, we can therefore say that the line does not meet the circle. So then we can return to think about what Brutus was saying. What Brutus was saying is that the line is a tangent to the circle, so he's saying it does meet it once. We've proven that the line does not meet the circle, so therefore Brutus is wrong. The next and final worked example I've put in red because I needed to illustrate the difficulty of this one. So we've got a circle with the below equation, x minus 6 all squared plus y minus 5 all squared equals 17. We're told that the lines L1 and L2 are each a tangent to the circle and intersect at the point 0, 12. So the tangents meet here. Find the equations of L1 and L2, giving your answers in the form y equals mx plus c. Now this is a bit of a nightmare question really. It's not immediately obvious really what to do. You might be thinking maybe I could find out the radius. Maybe I could use some geometry and think this is like a kite or something. Or work out the distance from this point down to where it meets the circle. Who knows? So it's actually quite an evil question, I think. The main tip for this lesson, for this question I mean to say, is it involves tangents to the circles. So that's your clue that it might involve discriminants. Another slight clue is we want equations for L1 and L2, and we want it to be given in the form y equals mx plus c. So what we could do is think about what the general equation for L1 and L2 would be. Well, we know the intercept of both of them is where y is 12. So we know the y-axis intercept is 12. So L1 and L2 will have a standard form y equals mx plus 12, because c, the y-axis intercept, is 12. So what we could try and do is substitute that y equals mx plus 12 into the equation of a circle. So let's see what happens when we try to do that. So the first bracket stays as it is. We have x minus 6 all squared. Then plus y, which in its general form is mx plus 12, if it's either L1 or M2. Whoops, didn't mean to close a bracket there. So that's y minus 5 all squared equals 17. So all I've done so far is subbed in the general form of the equation for either L1 or L2, which is mx plus 12 in place of y. So let's simplify slightly. So we have x minus 6 all squared plus, well, mx plus 12 and minus 5, that just becomes plus 7. That equals 17. Let's expand this out now and see what we can do with it. So if we expand out the first bracket, we'll get x squared minus 12x plus 36. If we expand this one out, we'll get mx all squared, so it's going to be plus m squared x squared. Mx times 7 and double it, so we get 7mx doubled to give 14mx. Square the 7 to get 49, and that equals 17. So already you can see what a big thing this is going to become. So let's simplify this a tiny bit in two different steps. I don't want to overwhelm. So let's just see here that we've got x squareds here and here. We have x's minus 12x and plus 14mx. We also have constants. We've got positive 36, positive 19, and a 17 on the other side. What we're going to do is rearrange this to be equal to 0. So getting the x squareds together, we have x squared plus m squared x squared. Then the x's, we've got plus 14 mx minus 12x. And the constant terms, 49, if we take away 17 from both sides, 49 take 17 becomes 32, plus 36, we're going to get plus 68. So all I've done so far is I've grouped together the x squared terms, I've brought together the terms involving the x, and I've brought together the constants to give us plus 68. What we can do here is now factorize out some things. So first of all, we have an x squared. So there's an invisible coefficient of 1 here. So we can think of that as being invisible 1x squared. So this we can factorize out for 1 and the m squared. So you have 1 plus m squared lots of x squared. Over here, for the x terms, we have 14m lots of x, minus 12 lots of x. So altogether that's 14m minus 12 lots of x plus 68 equals 0. We can now work out an expression for the discriminant of this, and because L1 and L2 are tangents, we know the discriminant has to equal 0. So for this awkward looking thing here, the discriminant is going to be b squared minus 4ac, where b is the coefficient of the x's, and so we know here that b has to be 4m minus 12. A has to be the coefficient of x squared, so a is 1 plus m squared, and c is going to be just 68 on its own. So b squared, we're going to have 14m minus 12 squared minus 4 lots of a times 68, so it's going to be 4 times 68 times 1 plus m squared. And that needs to be equal to 0, because the discriminant is equal to 0 when we have a tangent meeting the circle. So now we've got a big job in terms of simplifying all this. So I'm just going to take this here and move, to give myself more space, down here. So let's square out this 14m minus 12 bracket. So 14m minus 12 all squared. 14m squared will give me 196 m squared. 14 times minus 12 times 2, let's just check this on the calculator, shall we? So get away from stats mode. So 14 multiplied by minus 12 times 2, that gives us minus 336. So we have minus 336 m plus this minus 12 multiplied by minus 12, so plus 144. Then 4 multiplied by 68, so 4 times 68, that's going to give us 272. So we're going to have minus 272 and minus 272 m squared, all equal to 0. If we simplify now, 196 minus 272, that's going to give us minus 76 m squareds. We're going to have minus 336 m, and 144 take away 272, that gives us minus 128. And all that's equal to 0. Next, what we can do is move all of this to the other side, or we can multiply through by minus 1 to make all of these terms positive and just therefore a bit easier to deal with. So then we have 76m squared plus 336m plus 128 equals 0. Now at this point I'm going to let you off the hook, unless you want to be a Puritan and follow this through algebraically without using a calculator. It will factorise. I'll give you a clue, you can divide by 4. It'll factorise and you can drop out m without using a calculator. So if you're a Puritan, as an extension or a challenge or both, try this and finish it off without using a calculator. If you want a break, if you think this is a bit too hardcore, and it sort of is, it's an absolute mess, it's a giant question. I'm going to show you again how you can use a class whiz to help you do quadratic equations. It's much easier, and yes, you get a full credit in the examination as long as you're clear in what you're doing and what your solutions are. Unless a question says you must show blah blah blah. So read the question carefully, but it is possible to get full marks just by using the class whiz if you know what you're doing. So let's get this ready, and let's imagine we want to solve this now. So what we do is we go into menu and we scroll along until we get to this thing here, which is equation/func. So scroll along the menu like this until you get to where it says this. Press equals when you do. We want to solve a polynomial. This is a degree 2 polynomial. It's a quadratic in m. So press 2 and press degree 2 because the highest power of m is 2. It's a quadratic. Here you type in the coefficient of your variable squared, which is 76. Press equals. Next you type in the coefficient of the variable as it is, which is just 336. Whoops, too many 3's. And finally, you type in the constant term, which here we've got is 128. Press equals and equals again, and we'll work out what m is using the calculator. So, one option for m is that m might be minus 8/19. The second option for m is that the gradient is minus 4. So we can say therefore m needs to equal either minus 8/19 or minus 4. So using this, we know that L1, which is the steeper of these tangents, L1 must be the one with a gradient of minus 4. So L1 must be y equals minus 4x plus 12. Whereas for L2 is one which isn't quite as steep. So L2 is one with gradient minus 8/19. So for L2 we've got y equals minus 8/19 x plus 12. Because remember, again, like we set out this question, both have a y-axis intercept at 12, which you can see up here. So that's an absolute beast. To be honest, I would think you could count yourselves slightly unlucky if you encounter that in an exam, but what I've said before, I'll say again, the best practice is to do as many evil questions as you can. Push yourself, try ones that make you struggle, so that when it comes to the exam, you don't struggle. Struggle now, so that when it comes to the crunch in the exam situation, you've got your strength built up. And that's it from me. It's now over to you to try some of these yourselves. The suggested exercises today are found on page 122. Try questions 6 through to 12 on exercise 6D. You know the drill by now. Do a question, check it immediately. If it's right, move on. If it's wrong, try and see for yourself where you may have gone wrong and make your corrections. If you're not sure how you've gone wrong, ask somebody you sat near to or someone who's also doing maths. If you're still not sure, find me and I'll help you out. So thanks for listening. This is a hard topic, bear that in mind, it's not going to be easy all the time. So try these questions, do your best, and good luck. I'll see you for now.